Hey there. Let's do some analysis on the systems where there's a pulley involved. The first system we'll look at has a mass hanging on a cord that goes over a pulley and is attached to the wall. The second system has a mass that's hanging on a cord going over a pulley attached to a second mass that's on the table. So our first problem statement, an object of mass m hangs on a string over a pulley as shown. What is the tension in the cord? Let's start by stating the assumptions we're making. First, we're going to say that the string is massless and inelastic, and the second, that the pulley is massless and frictionless. The known variables and our desired answers, the next thing to consider. So here we know the mass of the hanging mass, and we want the tension. Next thing we do is draw a free body diagram of the block, and then we'll use that diagram to construct equations, and then solve those equations for the answer in terms of given variables. Here's what our free body diagram looks like. There's tension pointing upward along the string, mg pointing downward, two forces on the block, and since the block is attached to the wall through the string, it's not accelerating, it's not even moving, so the forces are going to be equal. So we have net force equals 0, there's no acceleration, equals tension minus mg. We've defined our y direction to be upward positive. That allows us to find the tension equals mg. Okay, now let's analyze a system that's a little more complicated. Our hanging mass is now not attached to the wall, it's attached to another mass. Our assumptions are going to be that there's no friction between the bigger mass and the table, and also no air resistance, besides the assumptions we had for the earlier problem. I'm going to draw in the direction of acceleration because it isn't the same direction for both masses. The mass on the table is accelerating to the right, while the mass hanging is accelerating downward. Start by drawing the free body diagram of this hanging mass. Notice that the tension is smaller than mg. That's because it's accelerating downward. Also, I've put the positive y direction in the downward direction for this mass to keep the acceleration positive. Now I've drawn the free body diagram for the mass on the table. It has a normal force pointing upward, mg pointing downward, and tension pointing to the right. The tensions have the same magnitude between the two diagrams, and I'm free to call positive upward for the mass on the table. We'll take our net force equation directly from our diagram. For the large mass on the table, the net force in the y direction equals 0, because it's not accelerating upward or downward. And the forces are the normal force pointing upward minus mg pointing downward. For the x equation, we have the sum of forces equals ma, because it is accelerating, and the only force there is t, as it's in the positive x direction. We take our net force equation for the hanging mass in just the same way. We have the net force in the y direction equals ma equals mg minus t. The mg is positive here because I've defined downward as being the positive direction. Now I want to take a look at these equations and see if I have enough to solve for the variables that I want. I have two known variables, both masses. I want the tension, and I can see that my equations include the acceleration and the tension in the x equation for the capital M and for the y equation for the small m. I'm not going to use my equation in y for the large mass. I would need to use that if I was including friction in this problem. So I think what I'll do here is I'll solve the x equation for the mass on the table for acceleration and substitute into the y equation for the hanging mass. If I solve the x component equation for acceleration, I get A equals tension over mass. Here I've substituted that into the equation for the small hanging mass, and then I've rearranged things to get all the terms with tension on one side. I factor the tension out of the equation. And finally, I get the answer I'm looking for. Tension equals little mg over quantity 1 plus little m over big M. Notice the units work out okay. The denominator is unitless, and mg has units of force, or newtons. Another interesting thing here is that it depends on the ratio of the two masses. Notice if the large mass gets very large, then the tension goes to mg because the denominator just goes to 1. Little m over big M goes to 0. That makes sense, because if the very big mass was extremely large, then the little mass would almost be like it was hooked right to the wall. So to recap, we've drawn free body diagrams of both blocks. We use those diagrams to construct the equations. Then we solve the equations for our answer in terms of given variables. Thank you very much for coming. Come again soon.